Hello dear colleagues, let me introduce myself. My name is Viacheslav Aseev. I am a graduate student at Southwest State University. My specialty is industrial and civil engineering. Today I'm going to talk about scientific work, which topic is methods for calculating rectangular cross-section beams made of timber and concrete. The purpose of this research consisted in studying methods for calculating timber-concrete beams of rectangular cross-section when testing building structures according to the ultimate limit state. The focus was put on the comparison of theoretical methods for calculating structures. The scientific novelty consists in the development of an algorithm for calculating composite timber-concrete beams of rectangular cross-section. As a result of the research, numerical comparison of the values for calculating a typical timber-concrete beam using two of the methods under consideration was given. Experimental studies were carried out as well as a comparative analysis of the obtained results of theoretical and experimental values. Let's touch on the relevance of the research topic. Nowadays, in many European countries, for the reconstruction or construction of new buildings, there is a growing tendency to share materials such as concrete and timber. This is explained primarily by the fact that timber is environmentally friendly. Concrete has high availability, as well as the presence of many other properties of these materials that effectively complement each other. The works of several researchers say that such constructive solutions as timber concrete appear to be beneficial for both the timber and concrete market. The former will benefit from the trend toward standardization and market expansion, while the second one will correspond environmental requirements and better differentiates in a competitive market environment. The work purpose consists in stress-strain state study of composite timber-concrete structures of rectangular cross-section. The aims were to develop a calculating method of bending timber-concrete beams based on the deformation model of section, to carry out analytical stress-strain state studies of bending timber-concrete beams based on existing and developed methods, conduct experimental studies of composite timber-concrete beams of rectangular cross-section under the action of short-term loads, and to develop an algorithm for calculating composite bending timber-concrete beams of rectangular cross-section, taking into account the comparative analysis of the experimental and theoretical studies results. So, there were considered two theoretical calculations. The features of the first one can be seen on this slide. Equation 1 shows that there is met the equilibrium condition of external and internal forces for the element under consideration. In other words, the sum of all forces projections is equal to 0. In this case, we determine that the height of the compressed zone is directly proportional to the tensile strength of the timber and the height of the timber element. Optimum performance of a timber-concrete beam is achieved when the ultimate moment for the compressed zone of concrete and the tensile zone of the timber are equal. The second calculation method implies the introduction of the modification coefficient n, which is the ratio of the elasticity modulus of concrete in bending to the elasticity modulus of timber in tension. In the calculations, we consider the loaded beam with concentrated forces in thirds of the span. Timber concrete beams has 1 meter length and section is 1000 by 75 mm made of. Concrete is equal to 50-75,000 mm. Timber is also equal to 50-75,000 mm. B15 grade concrete and 2nd grade pine are taken as the materials of the construction. Let's take a quick look at running an experiment. You can pay attention that figure 5, 6 and 7 shows 3 samples with different connection types. Such difference in their design was made intending to find the most optimal connection between timber and concrete. So, we transfer the load to the sample through a metal element, which mass is included in the total load. The load is transferred to the testing sample in thirds of the span. The plotted dependence graph, figure 10, clearly shows that the first sample was deformed linearly up to a load of 3.44 kN, and the third sample was deformed linearly up to a load of 3.68 kN. It is noteworthy that the second sample was deformed linearly up to a fracture which occurred at 5.28 kN. Linear deformation of the second sample may well be explained by the type of connection used in it, which turned out to be the most effective in the observed timber concrete beam, also allowing the structure to behave according to the conceived scheme longer and withstand more load compared to the other samples. Summing up the research, we obtained theoretical calculation and experimental studies results of a composite timber concrete beam of rectangular cross-section, and carried out calculating algorithm taking into account the comparative analysis of the results of theoretical and experimental studies. Based on a comparison of the theoretically obtained values and experimental data, we can see that the proposed calculation method allows to determine the critical values of the force F and momentum M of the considered type of structure. With this, I'd like to finish my speech and thank you for your attention.